Hello, everyone. Welcome to my paper presentation. My name is Iluan. I'm very happy here to introduce our paper and showcase our research work. Today, I want to talk about predicting stock prices, which has become a hot topic among investors, traders, and financial institutions. Even though significant progress has been made in predictive techniques, accurately forecasting stock prices is still a major challenge because of the volatility and complexity of financial markets. Plus, each stock has its own unique trends and variability. So, a method that works well for one stock might not work for another one. In our study, we're aiming to explore and compare the effectiveness of several advanced predictive models in forecasting NVIDIA's next-day stock prices. NVIDIA Corporation, an American multinational technology company, is famous for its graphics processing units, widely used in gaming, professional visualization, data centers, and automotive markets. The company has also ventured into AI, deep learning, and high-performance computing, establishing itself as a leader in these fields. We choose NVIDIA because of its leading role in the ongoing AI revolution, driving innovation across various sectors. Its recent performance in the stock market has also caught the attention of many investors. We evaluated four statistical and deep learning models: ARIMA, LSTM, multi-layered perceptron, and ARIMA-GARCH, to see how well they predict NVIDIA's next-day adjusted closing prices. Our dataset includes 5 years of adjusted closing prices for NVIDIA, from April 12, 2019 to April 11, 2024. From our results, you will see empirical evidence of how these models perform in terms of predictive capabilities. So, the first model is the autoregressive integrated moving average model, which is commonly used in statistics and econometrics for time series analysis. Unlike the autoregressive moving average model, ARIMA can handle non-stationary data. It has three components: the autoregressive component, which uses past values to predict future values; the moving average component, which uses past forecast errors to predict future values; and integrated component, which allows us to transform non-stationary data into stationary data by differencing the original observations. Next up is the multi-layer perceptron, a type of feed-forward artificial neural network. Like other ANNs, it has a feed-forward architecture with multiple layers, including input layers, which takes in the initial data features; hidden layers, which process data through weighted connections to learn patterns; output layers, which generates the final prediction or classification, all fully connected through weights and biases. Then, we have the long short-term memory networks model, which belongs to the recurrent neural network family. Unlike regular ANNs, which process input in a linear, feed-forward fashion without memory of past inputs, RNNs have loops that allow information to be passed from one step to the next, making them powerful for working with sequential data. LSTMs further refine the RNN architecture with three specialized gates: the forget gate, which controls the retention or removal of information from the cell state. The input gate, which regulates the addition of new information to the cell state. And the output gate, which determines what next to pass to the output layer from the cell state. Finally, we consider a hybrid model, the ARIMA-GARCH model, which combines the generalized autoregressive conditional heteroscedasticity model and the ARIMA model. The GARCH model is an extension of the autoregressive conditional heteroscedasticity model, useful for modeling and forecasting volatility in time series data by incorporating an additional term for lagged conditional variance. The dynamics of the mean of the time series are modeled through ARIMA, and its volatility is modeled through GARCH. Our data consists of 1258 data points in total. To evaluate the performance of various predictive models, we divided the data set, designating 90% in time order for training and the remaining 10% for testing. The training data set has 1132 adjusted closing price entries for NVIDIA, spanning from April 12, 2019 to October 10, 2023. And the testing data set includes 126 adjusted closing price entries from October 11, 2023 to April 11, 2024. We assessed the model's performance on the test data using three metrics: root mean square error, mean absolute error, and R-squared. RMSE calculates the square root of the average squared differences between predicted and actual values, making it sensitive to large errors. MAE, on the other hand, computes the average of the absolute differences, which means it's less sensitive to large errors since it doesn't square them. Finally, R-squared shows how well the model's predictions match the actual data points, with higher values indicating stronger predictive power. In our experiment, we set the integrated component of the ARIMA model to 1, because after first-order differencing the time series, the ADF test, which checks for stationarity, gives a p-value close to 0. This indicates that the first-order differencing made the series stationary. The ACF and PACF plots for the difference series suggest that small values for the autoregressive and moving average terms would likely suffice for accurate prediction. We then used an iterative approach to find the best autoregressive and moving average parameters for the ARIMA model, within a range of 0 to 4. We considered both expanding and rolling window approaches. For the expanding window approach, we initially used all historical data in the training set to build the ARIMA model. The best autoregressive and moving average parameters were those that resulted in the lowest AIC value, a common metric for model selection. The optimal ARIMA model then predicted the next day's adjusted closing value at time t, where t represents the first predicted value from the testing set. To predict the next value at time t plus 1, we added the actual value from time t into the training set, optimizing and retraining the ARIMA model with the expanded data. This process repeated until all predicted values from the testing set were generated. For the rolling window method, we first selected a window size n. Then implementation is similar to the expanding window approach, but with a key difference in the use of historical data. Instead of using an expanding dataset, the ARIMA model was optimized and trained with the most recent n-day observations from the training set to find the best model setup with the lowest AIC value. This setup was then used to predict the first value from the testing set. After this, we added the actual value from the testing set to the training set, re-optimizing and retraining the model using the latest n-day observations. This process was repeated until all test set predictions were made. With rolling window sizes chosen to be 30 or 60 days, the performances on the test set are shown in the table. Based on the result of mean absolute error, root mean square error, and R-squared value, ARIMA with an expanding window is the best model option. It was also later implemented along with the GARCH-11 model on the residues from the ARIMA predictions for the ARIMA-GARCH method. We focus on GARCH-11 models rather than higher-order GARCH models because they require estimating fewer parameters. Moreover, GARCH-11 is widely recognized in the literature as the preferred model for stock price prediction. Both the LSTM and MLP models were designed to forecast stock prices 1 day ahead using a sliding window method. For the LSTM model, the look-back parameter specifies the number of prior time steps including each input sequence for making predictions. The MLP model uses overlapping windows of a fixed size, corresponding to the look-back period, throughout the data series to organize the inputs. Each input window includes stock prices from consecutive previous days, with the output being the stock price on the next day. Before training any deep learning models, the time series data was normalized using the min-max scalar function in Python to enhance model performance. For high parameter tuning, the data set was divided into 80% training, 10% validation, and 10% testing sets in chronological order. Finally, the performances of all models on the testing set are illustrated in the figure and the table below. All models performed similarly well in terms of performance metrics. The ARIMA-GARCH model has the smallest RMSE and the highest R-squared. However, from the plot, you can see that the ARIMA-GARCH model tends to over-predict values towards the end of the testing set, which might be why it has a marginally higher MAE than the others. So, in conclusion, our comparative analysis reveals similar performance characteristics across different methodologies in general. The ARIMA-GARCH has the smallest RMSE, suggesting a lower incidence of large errors, but it shows suboptimal adaptation towards the latter part of the testing series. The ARIMA model with an expanding window approach generally demonstrates superior performance across all evaluated metrics, outperforming both the LSTM and MLP models. There might be various reasons for this. First of all, the NVIDIA series might not exhibit strong nonlinear patterns. Additionally, LSTM and MLP models are quite sensitive to their configuration settings, and these models might not be optimally tuned. The complexity of these models and the relatively small data sample might have hindered their performance. For future research, we could explore predictions that extend beyond the next day to assess how these models perform. Additionally, looking at a larger data set over a longer time period could potentially enhance the training process for the more complex LSTM and MLP models. Thank you for your watching.